Good afternoon, students, and welcome to practice assignment week 2 for nanotechnology in agriculture. So we'll be beginning shortly. It's already 3 p.m. I'll keep admitting students who are requesting to join. We can wait for 5 more minutes and then start our assignment discussion session. So it will be a practice assignment discussion session. For those who are attending this for the first time, what we'll be doing is we will try to solve a practice assignment corresponding to the weekly assignments that you have been given according to this course schedule, and we'll try to understand the logic behind how to solve the questions, which will help you in solving the actual assignment questions. We'll wait for a few more minutes, let's say 5 more minutes, so that some more students can join, and then we'll start the practice assignment. Welcome again, students. It's already 3:05 p.m. and I'll keep admitting the new students, but we have to start with the practice assignment session. So once again, to all the first newcomers and those who have already attended week one practice assignment, I would encourage you all to be consistent and please attend all the practice assignment, which will help you solve your actual assignments for this course. So what we'll be doing in this, what we'll be doing in this session. Hello. Yeah, I would like to first and foremost a few rules for smooth conduction of this session. I would request all the participants to please mute their mic and turn off their video chat. These are the two conditions we need to follow because there will be a lot of students, and for smooth conduction of the session, I would like to request all these participants to please mute their mic and turn off their video chat. And all the communication between me and the students will be through the chat box. So this will be an interactive session where I'll have a slide to present. So and then we can interact through the chat box. So this will be a practice assignment. I would not be answering any of your real assignment questions. So this is a practice assignment, and you have to do it yourself to score in the test. I'm just here to guide you. I'm just here to guide you all around the lectures and the basics of the assignments, so that in future if you face such questions or in your assignments, then you can solve it, right? So with that much of introduction, my name is Ashutosh Behera. I'm a PhD student, PMRF scholar from IIT Kanpur, and I'll be the TA for this NPTEL course, and I'll be sharing my screen now. Let's keep it as an interactive session and communicate through the chat box, right? We will solve together 10 questions in this 2 hour long session and see the rationale behind what and why the answers are correct or the answer correct option. So I'll just share my screen now, and I request again all the participants to mute their mic and turn off their video chat. If time permits, then we can take any extra questions, but we'll first try to solve the practice assignment questions. I'll be sharing my screen now. Just a minute. Yes. So students, is my screen visible? Is my audio clear? And can you see the slides changing? You can just type yes or no in the chat box to let me know. Please mute your mic and you can just type in the chat box if you can see my slides and the audio is clear. So we have yeah, we have around 65 to 70 participants, And I've got some responses. Yes, sir. Yes. So starting again, good afternoon, everybody. And this is the course NPTEL Nanotechnology in Agriculture. And we'll be dealing with practice assignment week 2. The course instructor for this NPTEL course is Professor Mainak Das from IIT Kanpur. And my name is Ashutosh Behra. I'll be the teaching assistant for this course. I'm also a PhD scholar at IIT Kanpur. So any course related issues and assignment related issues, you can directly email Professor Mainak Das or the NPTEL team. What I am here to help you with is the practice assignment week 2, where we'll try to solve similar kind of questions which you faced and which will help you strengthen your understanding. Right? Okay, so let's move on to the first question of the practice assignment. I'll read out the question for you. Which of the following is not sustainable? And the options are precision agriculture, hydroponics, excessive use of fossil fuels, organic farming. So now I would like the students to guess the correct answer or to hint the correct answer. So it can be wrong. Do not fear. Just try to attempt the correct answer. What do you think, according to you, is the correct answer? I'll wait for a minute. The students can type their answers in the comment box. And for people who have just joined recently, I was just introducing myself and the kind of assignment this course, this session would hold on. We'll be solving practice assignment questions. So this is not the actual assignment questions that you will be facing or you must have faced, but we will learn these practice assignments and see how to solve other questions or what are the rationale behind these answers. Okay, and I'm expecting some answers. Okay, there are lots of answers. Rashmi says 3, Vaishnavi 3, Soumyadeep C, Punit C, third option. Okay, so most of us have answered C. Let's see what's the correct answer. Exactly, all the students are very correct. Excessive use of fossil fuels is not sustainable, right? Let's see what the other options hold for us. So the first option we had was hydroponics. Yes, thank you, thank you. Nice. We need this kind of participation on every question. So I'll open the question for you and give some time for all the students to guess the answer or predict the answer. Then you'll see if the answer matches with the correct answer. And we'll study about what other options could have been possible and why the correct answer is the correct answer. Right? Yes. So the three options that we had was precision agriculture, hydroponics, organic farming. So we'll study about a little bit about what is hydroponics. As the name suggests, hydro means water and ponics means plant growth. So growing plants, usually crops or medicinal plants, without soil by using water-based mineral nutrient solution in aqueous solvents. So here, as you can see, this is a hydroponic farm or a greenhouse in which all these plants are growing in a soilless environment. There is no soil for the plant to attach to and grow. Besides, as an alternative, the plant roots are connected through this long tube pipeline through which nutrient mixed water is passed on and circulated, water-based mineral nutrient solution in aqueous solvents. So there are solvents, there are many nutrients, whatever the plant requires for its growth, supplied in this pipe, and this water circulates everywhere. So the plant can directly absorb through its root from the pipeline, and there is no need of soil. And this is such an advanced technique of soilless agriculture, and definitely it's very sustainable because hydroponics offer many advantages. And one of the best noted advantages is decrease in water usage. Now you must be saying that, sir, how can it decrease the water usage? It's only based on water, nutrients, and solvent. But the real scenario is, if you compare to grow 1 kilogram of tomatoes using intensive farming methods, means using the traditional farming methods where we supply water, fertilizers with the soil, requires 214 liters of water. Using hydroponics, only 70 liters. So this is the soil water usage. If we grow 1 kilo of tomatoes, we need 214 liters of water. But in hydroponics, it's drastically reduced, almost one third of the volume. So 70 liters of water can now be used to grow 1 kilogram. So hydroponics offers the biggest advantage of decrease in water usage. That's why it's very sustainable and energy friendly and environment friendly. And the next point that I wanted you to focus, not only used on Earth, but also has proven itself in plant production experiment in space. Since we do not require soil for hydroponics, we can use this pipeline system to supply water-based mineral nutrient solutions. It has also been successfully worked out in space. In space stations, there can be hydroponic system growing out plants. See what high potential this hydroponic system is holding. Even in a soil-less agriculture method, it lessens the water usage, and it has also been successful in space where there is no soil. So it's definitely a sustainable form of agriculture and very eco-friendly. So this could not be the right answer to our question, which was not sustainable. And the next method is precision agriculture. Now, what do we mean when I say precision agriculture? Precision agriculture includes drones, global positioning systems, and irrigation technology. So precision agriculture means we precisely acquire data of all the crops and the type of soil. Individually, we process the data. Then accessing the data, we make decisions to individually improve the crop and taking action. So it's like more planned and more organized way of doing agriculture. So each and every crop has different requirement. Each and every soil type or geographical area in which the crop grows also have different properties. So accessing everything and analyzing everything to design the best management strategy is known as precision agriculture, which didn't exist in the older times. In the older times, there was no precision agriculture because people didn't take into account so many factors which are variable. So many different crops have different needs and requirements and have lots of variability factor, also depending on the weather conditions and the soil type. So we use these modern technology like drones for spraying fertilizer and pesticides, global positioning system, and irrigation technologies. Good irrigation technologies, sprinkler technologies, and drip irrigation. And the goal of precision agriculture is to learn new management practices to increase the profitability of agriculture production. So all this precision agriculture that we are getting to see is to maximize the agricultural production with good management practices and to benefit. So humans always want benefit. With less space we'll have more produce and more effective health of the plant or the crop, then we'll have more profits. And using all these techniques for precision agriculture we can achieve it. And the third option we encountered was organic farming. Now what is organic farming? Organic farming is the method in which there is no reliance on any kind of external agent like chemical fertilizers, pesticide, insecticide, nothing, not even genetically modified organisms. So organic farming does not depend on any kind of external factor. Everything needed in the crop or in the farming field comes from the nature and surroundings itself. So by definition, organic farming is production of food and livestock. Livestock means cattle. food and any food crops without the use of chemicals like herbicides, pesticides, weedicides, fertilizers, or genetically modified organism, and use natural resources such as manure and compost. So the main two pillars of organic farming are manures and vermicompost. Earthworms in compost pits, all these plant produces, the kernel and the waste products, these earthworms will vermicompose them, produce manure. That manure is then recycled again to the field to enrich the field. There is no need of fertilizers. There are something called biofertilizers, means these manures and other earthworms where they are designed and they can be applied to the plant. All natural based, no chemical, no use of chemical, herbicides, and even biologically modified organisms. Right? That's how organic farming operates. So now we are clear that organic farming is a production system which maintains the quality of soil ecosystem as well as human beings. So all this organic farming maintains the quality of soil ecosystem because there is no external fertilizer used, there is no genetically modified organism used. So all occurs in the nature. We are not harming the environment in that way. So now we came to learn about three different techniques: hydroponics, precision agriculture, and organic farming. And all three are very sustainable, while dependence on fossil fuels, which was the correct answer for this question, excessive use of fossil fuels is not sustainable, right? So, is it clear to the students? The first question, answer, and the explanation? If yes, you can just type yes in the chat box. And for the students who have joined just now, we have just begun the first with the first question of practice assignment, where we'll be solving 10 different questions with while in interactive manner. I will request all the participants to please switch off their mic and turn off their video chat. You can interact with me via inbox chat messages. So I was just asking the present students to guess the answer for the first question, and it was C, the excessive use of fossil fuels. So is it clear to the students? You can just type yes in the chat box. I'll be just waiting. Yes, 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 good. Okay, there is a question. The ball milling process involves what basic technique? Rashmi asks. So Rashmi, please have some patience. There are questions which will be dealing with ball milling process and we will go through it very extensively. You just have to hold your horses and let's go with the flow, solving each and every question, right? So let's move on to the next question. Good. I'm very happy to see that there is a lot of participation in the chat box. So I would request all the students to participate actively in this discussion. It's not a one-way discussion where I'll be teaching and you'll be listening. We will both together try to solve the questions and then look at all the possible answers and options and find out why the possible answer is the correct answer. Cool. Let's move on to the next question. Okay. Can you guys see the next question? I think, hello. Can you guys see the slide changing? Yes. Yes, right? Yes, yes. So the next question that we'll encounter, I'll read it out for you. Which of the following is smallest in size? Right? Which of the following is smallest in size? The options are quantum dots, nanotubes, nanoparticles, nanocages. Come on, students. And I'll wait for answers in the chat box. Please type whatever answer you think is correct. Do not shy out. It's okay if your answer is wrong or if it's close. There won't be an issue. We will decode the answer, that why the correct answer is the correct answer. Right? Just try to answer. Which of the following is do you think is smallest in size? Quantum dots, nanotubes, nanoparticles, and nanocages. I'll wait for a minute and see all the responses. Meanwhile, I'll just request all the participants to please mute their mic and turn off their video chat. Any interaction with me will be through the comment box. Okay, there are already some answers. Vaishnavi says A. Rashmi may be first. Soumyadeep A. Vishnu Priya is going for nanoparticles. Shweta, Mahinder, Haripriya A. Chaitanya A. Vajanti A. Students are still joining. I'll keep them admitting. Come on, we have almost 90 participants. We need more answers, right? There are already students who are participating. I'm very happy about that. Very good. And others, please try to answer whatever you think is the correct answer. Which of the following is smallest in size? Quantum dots, nanotubes, nanoparticles, nanocages. And the participants who have just joined now, please turn off your video chat and mic. You can interact with me through the chat box where we'll be discussing these questions together and see what is the correct answer. Right? Okay, we have enough answers. So most of the people say A. There are few answers which also go for C. There are two school of opinions: quantum dots and nanoparticles. Let's see what is the correct answer. The correct answer is A, quantum dots. And congratulations for those who have answered A. For people who with C option, you were close. But let's see what are the size differences for all these nanoparticles, right? So here is a size scale bar. I hope you can see them. Here is a size scale bar which shows the ranges from zero point 0.1 angstrom to meters. In all, in 10 to the power minus 10 is the angstrom level. 10 to the power minus 1 is around meters level. 10 to the power minus 1 meter to 10 power minus 10 meters, right? And here you can see nanomaterials are known as nanomaterials because they fall in the nano range. 10 to the power minus 9 range of 10 to the power minus 9 range of size, right? And this gold nanoparticle here is an example of nanoparticle. Its size is from 10 nanometer. Carbon nanotube, the diameter of carbon nanotube is 5 nanometers. Benzene here is the carbon molecule, 0.5 nanometers. So all the nanomaterials fall in this range. And incomparable to the water molecule, which is in angstrom level, viruses which infect our biological systems are in the micron level, 1 micron. Red blood cells is 5 micron in diameter. A full stop from the pen is 1 millimeter, while a hair is 100 micrometer thick. A coin is dimension of 1 centimeter, and this is a watermelon just to represent the size. So we understand that all nanomaterials fall in this range. Now, what makes them very different? So this is an example of silver nanoparticle. It's an example of nanoparticle, and this ranges from size 1 to 100 nanometers. And here is a representation of nanocages whose size ranges from 10 to 150 nanometers, right? And this is the another nano structure, nanotube, whose size ranges from 1 to 100 nanometers. And finally, quantum dots, which are very small. Quantum dots size range from 2 to 10 nanometers. It can also range in the if we measure by number of atoms, range of 10 to 50 atoms. So quantum dots are the smallest nanostructure, smaller than nanoparticle. Nanoparticle is close. We can have 1 nanometer small nanoparticles, but generally we have in the range from 1 to 100 nanometers. Nano cages and nanotubes are complex arrangements of nanoparticles and fibers. So all this must have been mentioned in week 2 lectures where Professor Mainak Das was talking about classification based on shape, sizes and geometry, right? So the correct answer would be, as many people guessed and answered, quantum dots are the smallest among all the nanoparticles. It's not nanoparticle, nanocage and nanotube. So the answer would be quantum dots, correct? So students, is this second question clear? You can please type yes or no in the chat box. And people who have recently joined, please try to participate in this practice assignment where we'll try to solve questions together. Students, is this clear? I'll just wait for a minute for your responses. And for the new joinees, I would just like to repeat myself. Please switch off your video chat and mic. You can interact with me or through this session. Throughout the session, we'll be interacting through the chat box for smooth conduction of this session. So is it clear for the second question? Then we can move on to the next question. Okay, my screen did not change, Soumyadeep says. I'll just recheck my internet connection. Please bear with me for 5 seconds. I'll just escape out and check my internet connection. I think it's connected. So I'll just test it once again. Can you see my slides changing? I'm on slide 3 now. Question number 3. You can just type yes or no. Okay. Uh, I think there is some problem. Just wait. Bear with me for a minute. I'll just try to. I'll try to share my screen again, and we'll begin from slide 3. Right? You can try that. Yeah, I have stopped presenting, and I just start representing again. Sorry for the inconvenience. I'm just trying to present my screen again. Please bear with me. Oh no, the meeting. I'm just trying to rejoin the meeting, students, through my laptop. Just just wait for a few more minutes. I don't know what's the some technical problem might be. I'll be able to present really soon. Hello students, I think my connection is back. I'll present my screen again. Yeah, we are back. We are back again. Just me just yes. I think it's smooth now. I hope so. Yes, students, can you see slide number 3 where we have a question? If yes, you can just type yes. Sorry for the delay. There was some problem from my side. We can just quickly start solving question 3. Is my slide visible? Audio clear enough? Okay, yes, yes, yes. Okay. Okay, fine. Nice. So the third question, I'll just read it out for you. Which of the following nanomaterials can be categorized as carbon based? And there are already some answers. It's good to see that there are so many smart people here, right? And very active. Which of the following nanomaterials can be categorized as carbon based? Options are iron pyrite nanoparticles, graphene, molybdenum sulfide nanoparticles, all of the above. So I'll just wait for a minute for people to answer, although there are already some answers. I think it's a pretty easy question, like logical. People are saying B, option 2. I would like all the students to try to answer. It's okay if your answer is wrong. We just need to actively participate to understand the basics of this course. Please, all the students, so there are lots of students here. I would request all the students to try guessing this answer or try finding out what is the correct answer. I know all of you guys will be able to answer these questions. Just please show some confidence and type it out in the chat box. I'll be waiting for some more time. Yeah, some responses are coming up. Let's check what is the correct answer. The correct answer is B, graphene, and all the students have answered very well. Good, so good. So graphene is a nanomaterial that can be categorized as carbon based. So this is a direct question from the lecture series. If you would have gone through week 2 lecture series, let's see about what kind of other nanoparticles we have. So if we classify nanoparticles on basis of their chemical nature, we can classify them into organic nanoparticles, inorganic based nanoparticles, and carbon based nanoparticles, right? And then organic based nanoparticles, I have listed some examples here. These are not the total list or current examples. So there are dendrimers, there are liposomes, micelles, and all sorts of proteins, protein nanoparticles also, DNA based nanoparticles. Inorganic based nanoparticles consist of many other branches, but I was just listing two of them which are relevant to us: metal based, metal oxides based, metal sulfides based, And the iron pyrite here means iron sulfide, which formula stands for FeS2. Iron pyrite is a metal sulfide based inorganic nanomaterial. And molybdenum sulfide is also a metal sulfide based inorganic nanomaterial. So that leaves out these two options. Iron pyrite nanoparticles would not be the answer. Molybdenum sulfide would not be the answer also. So the answer is graphene, which is a carbon based nanoparticles. So carbon is so versatile that carbon based nanoparticles um, have its own range, where we have graphene, carbon nanotubes, and many other structures like diamond, fullerenes. Fullerenes are also nanoparticles, fullerene based nanoparticles. And we have graphene, carbon nanotubes, carbon fiber. So iron pyrite and molybdenum sulfide will fall under metal sulfide category, while graphene will fall under carbon based, right? So this is how iron pyrite looks like. Iron pyrite is mined in the ores as this rock cubic formation of crystals, and this is how molybdenum sulfide looks like, mica silvery appearance. And the correct answer, which is graphene, is carbon based. So in graphene, we have also discussed graphene at length in the first weekly practice assignment. Graphene is consist of Graphene consists of carbon atoms arranged in hexagonal honeycomb structure. So this mesh network is hexagonal, as we can see here, and joined by covalent bonds. And the special feature of graphene is there are double bonds also. So graphene forms a layer when the carbon atoms arrange themselves in a hexagonal honeycomb layer, also alternating with double bonds, we form graphene, right? And these multiple layers of graphene can then be arranged together to form graphite. So graphite has a structure in which multiple layers of graphene, these benzene kind of structures, are arranged, and that forms the graphite. So graphene is the correct answer, carbon based nanomaterial, which was option B, and many students answered it correctly. So students, is question 3 clear? Is the explanation clear? You can just type yes, no in the comment box, and we'll move to the next question. It was pretty easy, the question 3, which is carbon based. There are already metal names mentioned, iron pyrite and molybdenum sulfide. So it would click to everybody that these are metal based nanoparticles rather than carbon based. So is it clear? You can just let me know in the chat. Yes, yes, yes. Good, good. Great. We are moving great till now. We have finished the third question. Let's move on to the fourth question. So the fourth question, I'll read it out for you. Which of these fall under the categories of rare earth metals? Which of these fall under the categories of rare earth metals? Options: iron, zinc, copper, cerium. Students, please try to answer. Even if you're guessing it, it's totally fine. If your answer is not correct, we will understand the rationale behind the correct answer, which will help you in solving your assignment. And I think most of the students would be able to answer this question very easily. I'll repeat the question. Which of these fall under the categories of rare earth metals? Iron, zinc, copper, or cerium? There are 90 participants. I at least expect 50% of students to try to answer. Then we'll increase this 50% to the 100% in the following upcoming questions. Come on, these are easy questions. Students, just try to type out the option number or the answer in the chat box. I'll wait for a minute. Great. So there are many answers. Many answers now. D, 4, cerium, D. Okay, so most people are answering D, option 4. Yes, good. The participation is increasing. And let's see what is the correct answer. Yes, you guys are all correct. It's cerium. So iron, zinc, copper, and cerium. Out of these, cerium is the rare earth metal. Now here is a schematic of periodic table. Yeah, I would just like to reiterate again. Please switch off your mic and video chat for a smooth conduction of this session. We can have all the interactions via the chat box. Okay. Yeah. So this is a periodic table showing all the groups of elements. And so the first option, iron. Iron with atomic number 26 falls in this D block or transition metal zone. Transition metals, this purple colored. Copper, zinc are nearby. Copper atomic number 29. Zinc is just succeeding copper. Zinc atomic number 30. And cerium, here is cerium, atomic number 58. Cerium is the first element. Cerium is the second element of the lanthanoid series. Technically the second. If you consider lanthanum or La or Ln 57, so cerium is the lanthanoid series elements, right? Rare earth elements. And cerium, if you remember quite the lecture from week 2, cerium is used in the form of cerium oxide, categorized under rare earth oxide based inorganic nanoparticles. So cerium is used in cerium oxide form, metal oxide based nanoparticles, and with atomic number 58, it is the first element of lanthanoid series to look at. So cerium oxide nanoparticles, this is the formula for cerium oxide, CEO2. And this type of nanoparticles have many applications in the field of medicine and biology. Antibacterial properties, fragmentation of chromosomes. So this can cause fragmentation of chromosomes in bacteria. Drug delivery system, inhibition of enzymatic activity, antifungal activity. It can inhibit the ATP synthesis in fungus, can deal with oxidative stress, anti-diabetic activities, peroxidation of plasma membrane. So in diabetes, this can function by peroxidation of plasma membrane. Anti-cancer effects, where inhibition of signaling pathways which cause the cancer. So for triggering of cancer, cancer is just uh, cancer is just a normal cell which has its cell cycle activity impaired. So the cell does not know when to stop dividing. That's why the normal cells keep on dividing, and keep on dividing to form a mass of cells called a tumor, which we see in cancer. So there are many signaling pathways controlling this cell division and other properties of cancer. These cerium oxide nanoparticles have been used to deliver anti-cancer inhibitors, where these signaling pathways can be inhibited. Antioxidant properties, again, to antioxidant property to protect the mitochondrial ROS production and damage. By ROS, I mean reactive oxygen species, which generates in the cell due to hypoxia and toxicity. So antioxidants can just so tomatoes and all contains a lot of antioxidant which help us fight these ROS signals. Similarly, cerium oxide nanoparticles can carry antioxidant to counter the mitochondrial damage, and it can also cause degradation of DNA in pathogens like bacteria and fungus. So these are some of the applications of CEO2, cerium oxide nanoparticles, which is one of the rare earth metal based oxide nanoparticles. Right. So is it clear to the students? You can just type in the chat box I'll wait for some responses. Is it clear for the students? Rare earth element cerium is the answer. Iron, copper, and zinc are transition metals, we saw. We also learned about some of the applications of cerium oxide nanoparticles. So all these sessions, there is a question in the chat, when will the recording video go to me? So all these sessions are recorded. I'll upload it on my YouTube channel, and the YouTube link will be shared through NPTEL to all the participants in the course. All these presentations will also be shared through you through the Google Drive link, and this session is recorded. It will be on the YouTube channel, and through the NPTEL nanotechnology course you can access this. I'll be uploading it in a common drive, so you won't miss it. Yes. Okay, so we have completed question 4. Moving on to the next question. The next question is, using DNA as a template for nanoparticle synthesis is a dash approach. Top down approach, bottom up approach, both A and B, none of the above. I'll repeat, using DNA as a template for nanoparticle synthesis is what kind of approach? Is it a top down approach, a bottom up approach, both A and B, or none of the above? Student can take the time and try to answer this question. I'll wait for a minute. Let's wait for maximum responses. What do you think would be the correct answer? Using DNA as a template for nanoparticle synthesis. What kind of approach is this? Few people have answered option A. Let's wait for other students to answer. What do you think will be the correct answer? Using DNA as a template for nanoparticle synthesis, is it a top-down approach, bottom-up approach, or both A and B, both top-down and bottom-up, or none of the approach? It's another type of approach. Okay, some answers are saying B. So there is conflict between top-down approach and bottom-up approach. Students, you should come forward and answer this question. Participate in this practice assignment session and try to recall your lectures. It's all mentioned in the lecture and it will help you actually understanding this course and moving ahead with your own assignments. We have many participants and I'm waiting for some more answers. Please just type your answer in the chat box. Okay, it seems like there are two answers. People are opting for A, top-down approach, and B, bottom-up approach. Let's see what is the correct answer. The correct answer is B, bottom-up approach. Using DNA as a template for nanoparticle synthesis is a bottom-up approach for nanoparticle synthesis. So to understand this answer, let's see what is a top-down approach and what is a bottom-down approach. Bottom-up approach. Sorry. So we'll just go slowly through this. Top-down approach. In top-down approach, we start with bulk of the material. So there is always bulk material as a starting in top-down approach. And we break down this bulk material by using energy. We powderize it, pulverize it, break it into smaller fragments, transformation into smaller fragments, and then this can exfoliate of multi-layers to monolayers. So all this is like top to down approach. So bulk to nano approach, bulk to powdered. You just grind it or break it down into smaller pieces and break it down, keep breaking it down till it reaches the nano scale. Then it can exfoliate in multi-layers to monolayers. Exfoliation means it can layer off, can layer off as a nanomaterial. So we start with bulk and go to we start with bigger size and go to the smaller size is known as top-down approach. But in bottom-up approach, we start with smaller size and then go to the nanoparticles, right? So that's the difference between top-down approach. In bottom-up approach, the precursor containing molecules are very small in size already. So we do not start with bulk material. And then we use energy, ionization, maybe radicals and electrons to form an environment where all these precursor molecules can undergo self-assembly or condensation or formation of clusters. So we have starting materials, we provide them with some kind of energy and an environment to undergo self-assembly into a nanomaterial. So that is bottom-up approach. While in top-down approach, we have a bulk material, we break it down into finer and finer and finer particles and move into the nanoscale. That's how top-down approach works. While in bottom-up approach, we have a precursor molecule and we provide it conditions for its self-assembly. So here the answer, the question that was asked, using DNA as a template for nanoparticle synthesis. So if you see, DNA is a precursor molecule, is coinciding with this precursor containing molecules, and we are just providing an environment for the DNA nanoparticle synthesis to form self-assembly and clusters. It's not a top-down approach because DNA is not a bulk material. DNA is not big in size. We cannot break DNA into smaller nanoparticles, right? We are not going to break DNA. We are using DNA as a template to synthesize the nanoparticles. So the answer would be bottom-up approach. So see here we can, the schematic shows bulk to small nanoparticles. There can be different kinds of nanoparticles, fullerenes, diamonds, graphene, nanosheets. And these sheets can also be formed from bottom-up approach where we have precursor containing molecules, condensation to form clusters and self-assembly, and then we can form graphene and nanosheets. So as an example of DNA, using DNA as a template for nanoparticle synthesis, we have something called DNA hydrogel. I hope everybody must have heard this term DNA hydrogel. You can come across it in many tissue engineering papers or articles and in news also. It was quite trending. DNA hydrogel is a form of nanoparticle or a nanomaterial in which DNA is used as template, and there are primers. AUNP means gold nanoparticles. So these nanoparticles are added onto the DNA with PCR primers, and in PCR conditions, these primers attach with the DNA and multiply them, while gold nanoparticles then attach with these DNA ends and then form a mesh-like structure, DNA gold nanoparticles gel network. And this is an example of DNA hydrogel, gold hydrogel formation. DNA and gold nanoparticles hydrogel. DNA hydrogels can be fabricated through either chemical linkage of DNA molecules or physical entanglement between DNA chains. So here we saw chemical linkage of DNA molecules to the end of gold nanoparticles. Otherwise, there can also be physical entanglement between DNA chains, because if there is lot of amplification of PCR and there are nanoparticles involved, the replicated amplified strands can physically entangle between themselves and cross-link to form a DNA hydrogel. By other chemical approaches, the polymers are bound together through covalent bonds which endow environmental stability and intensive mechanical strength. So what happens? These polymers containing of all these cross-linked and mesh work of DNA, amplified DNA along with gold nanoparticles are bound together through covalent bonds with environmental stability and intense. So these interactions provide lot of mechanical strength to the DNA hydrogel. That's why it can be used as a ground material or a substance for releasing the DNA on time whenever it's required, and it also forms a basis for many biomaterials. So if you see the application of DNA hydrogels, DNA hydrogels can be used for loading drugs onto it, like functional biomolecules, small molecule drugs or inorganic materials can be transferred into the DNA hydrogels, which can then be used for different biomedical applications like chemotherapy. We can add small molecule drugs for which can target the cancer cells, and the delivery agent will be the DNA hydrogel. This can take this drug of chemotherapy to the cancer cells and kill them. Immunotherapy, where we have antibodies and other blood-borne secretions which can help in controlling the immune system. Gene therapy, where we have genetically modified DNA transfer. So we have a gene mutation modified outside in vitro systems. We transfer it to the DNA hydrogel, and this DNA hydrogel then can be applied to the patient, where this DNA hydrogel will release the good copy of the DNA and cure, kind of provide a balance for the mutated copy. So that's how DNA hydrogels have been used in various biomedical applications like chemotherapy, immunotherapy, and gene therapy. So the answer for the question that DNA based using DNA as a template for nanomaterial synthesis, what is the approach? The answer would be bottom up approach, because DNA is small in size, and we use it as a template. We give it conditions like these for self assembly and cluster formation of nanomaterials. So DNA template nanoparticle synthesis would be bottom up approach, not the top down approach, right? Yeah. So is it clear to students? Is it clear to the students? Then you can just mention in the chat box. I hope the basic difference between top down and bottom up approach was understandable, because this concept is really important. Then we will move further to see what kind of top down and bottom up approaches are available, which will be in the upcoming questions. So is it clear for the students that DNA template synthesis would be a bottom up approach? Yes. Okay, good. Moving on to the next question. So next question is really related to what we have understood in the previous question. Grinding down a bulk material into smaller particles of nano size is a dashed approach of nanoparticle synthesis. Grinding down a bulk material into smaller particles of nano size is dash approach of nanoparticle synthesis. If participants have paid attention to the previous problem solving, this would be easy for them. Options are top down approach, bottom up approach, both A and B, none of the above. It's pretty direct, right? Yeah. Students are answering A. So A is the right answer. Top down approach is again grinding down a bulk material. So grinding down is a method for top down approach, but the concept here is you are breaking a bulk material into smaller particles of nano size, and this is a top down approach of nanoparticle synthesis. While in the previous example we saw an example of bottom up approach using DNA as a template for nanoparticle synthesis. So again here I'm listing some approaches, some methods used for top down and bottom up approach. So as you can follow, so in this top down approach, here in the green sphere we have bulk material. This bulk material is further reduced in size broken into smaller particles until we reach the nano level of size. So that is top down approach, breaking down bulk material into nanoparticles. And there are various methods. We have mechanical milling, etching, laser ablation, sputtering, electro explosion. So these are all examples of top down approach method of nanoparticle synthesis. While on the contrary, we have a comparison of bottom up approach, where at molecular atomic level we have these starting materials. There is something called nucleation and growth, which will grow it into the nanoparticles. So all these starting materials here will be provided with a apt environment for the reaction to happen, where these can cluster together, as we know, cluster or self assemble together. That process is called nucleation. The starting process of uh, clustering and self assembly is called nucleation. So nuclei, such nuclei will form, which will act as centers for assembling of nanoparticles. And then finally we'll reach the nano stage, where we'll synthesize the nanoparticles. And these are some of the methods, popular methods for bottom up approach: supercritical fluid synthesis, spinning, sol-gel process, laser pyrolysis, chemical vapor deposition, molecular condensation, chemical reduction, green synthesis. So you guys need not worry about all these technical terms. We will go through in the upcoming questions. We will go through some of the techniques, some from the bottom up approach and the other from the top down approach, right? So if you analyze it further, top down approach describes that nanoparticle synthesis from bulk material into smaller ones. Again, and top down strategy mostly falls under the physical method of nanoparticle synthesis. Why? Because it acquires big tube furnace to smash bulk material into smaller parts. So in the top down approach, when we what we use here is force or some kind of energy to break the bulk material into finer pieces. So it's mostly physical method of nanomaterial synthesis, because we need force and mechanical energy and thermal energy and electrical energy to break down the bigger bulk material into smaller nanoparticle size. While in bottom up approach, we do not need physical methods. We need biological and chemical synthesis, in which nucleation reaction can proceed from the starting material to form clusters and self-assembly of nanoparticles. Right? So this was the technical difference between top-down and bottom-up approach. And the answer to our question would be grinding of the bulk, grinding down a bulk material into smaller particles for nano size is a form of top-down approach. Is it clear to the students? You can just mention in the comment box. We are moving fast. We've already reached the sixth question. Is it clear to the students? So I want you guys to permanently store this in your mind. What is the basic difference between a top-down approach for nanomaterial synthesis and a bottom-up approach? So that further you would not get confused and use your logic of understanding these both approaches, right? Okay, there are some responses. Yes. Next question, question number 7. Which of these is not a physical method of nanomaterial synthesis? Which of these is not a physical method of nanomaterial synthesis? High energy ball milling, option A. Option B, polyol synthesis. Option C, electrospraying. Option D, all of the above. So to answer these questions, you need to have basic knowledge of what are the different methods for nanomaterial synthesis. We just learned about two different approaches, the top down and bottom up approaches. There is another classification for the different kinds of methods for synthesis. So which of these is not a physical method of nanomaterial synthesis? I'll wait for a minute for students to answer. Please students just try to answer, even if you answer it wrong, it's totally fine. Need not be ashamed of. Be confident. Type the answer in the chat box. What do you think is the answer for this question? Which of these is not a physical method of nanomaterial synthesis? I'll wait for some time to for students to answer. Yes, we need more participation. There are some students who are faithfully answering and participating in all the questions. We just need more students. Please try to recall your lessons from week 2, and which of these is not a physical method of nanomaterial synthesis. Even if you apply your logic, it will be very easy uh, to just find out the option which will be a physical method and which is not a physical method. Okay, we have some answers already. Unanimously, answer goes for option B. Option B, polyol synthesis. Okay, so many answers. Option B, polyol synthesis. Let's see what is the correct answer. You guys are absolutely correct. The answer is polyol synthesis. Polyol synthesis is not a physical method of nanomaterial synthesis, right? While high energy ball milling, electrospraying are all forms of physical method of nanomaterial synthesis. Let's deal with them in detail. Okay, sorry. So if we start from basics, what are the different physical methods we use for nanomaterial synthesis? And as we have already understood, most of the top-down approach uses all these variety of physical methods. So there are four different varieties of physical methods. We can either apply mechanical pressure on the bulk material, high energy radiation on the bulk material, thermal energy or electrical energy. So wherever we use mechanical pressure or radiation, heat and electricity to break down a bulk material into a smaller nanoparticle to the nano size, those all are classified under physical methods in top-down approach, right? So in physical methods, you mostly see top-down approach. So any of these applications, mechanical pressure or high energy radiation, thermal energy, electrical energy, are all coming under physical methods. Now looking at the first option, high energy ball milling. I remember at the start of the session, there was a question in the chat. So what is the mechanism of high energy ball milling? So here we are. Let's discuss thoroughly. So as you can see in this diagram, this is a big ball, double layered, as you can see. And inside of this ball, there are certain smaller balls. So these are rolling balls. And these rolling balls, in between them, all these black dots that you see, these black dots are the materials which these balls grind. So what happens when this outer bigger ball rotates? So inside them, all these small balls will roll along with the bulk material and then churn it into pieces. It's basically grinding bigger material into pieces. And with the to and fro motion of this bigger ball, the double layered ball that we see, when this ball rotates like this, there is centrifugal force. The force motion is showing here. Centrifugal force directed towards the center and movement of the supporting disc. So there is a disc here. The supporting disc will move like this, and all these balls will roll along with the materials to break down the bulk material into into smaller sizes. So rotation of the milling ball will be in this direction. When uh, when mm, when the bigger ball will move in the clockwise direction, rotation of the milling ball will be opposite because all these balls will roll in the anti-clockwise direction, right? If you imagine a bigger ball and few small balls inside them, that will be the kind of movement. And while rolling through the bigger ball, these small balls will collide with each other and grind the bulk material into smaller pieces. Materials used to grind include iron ore and ceramics are added to the ball mill. So inside the ball mill, iron ore and ceramics are also added to increase the friction and mechanical pressure inside the mill, so that these rolling balls will have more force generated and then dash against the bulk material and break it into smaller pieces. It rotates either on its vertical or horizontal axis and bounces around while striking the enclosed material. So all this opening, there is no such opening, is just for the depiction. So all this happens in a closed ball container like a ball bearing, and the rotation can be either along horizontal axis, this the horizontal axis in the x-axis, or in vertical axis in the y-axis. So anyway, the whole ball can rotate, and accordingly, the rolling balls inside the ball mill will rotate in the opposite direction and then churn the material. So it rotates either on vertical or horizontal axis and bounces around. So the ball are also bouncing on the bulk material while striking the enclosed material. The force of the strikes helps to grind materials into fine, less coarse medium. So when these balls will bounce and strike the bulk material, that mechanical force helps to grind the materials into fine and less coarse medium. So once the bigger rock uh, turns into dust, all this will be fine, less coarse medium. And nanoparticles are much lesser in size than dust particles. So we need fine to less coarse, fine grinding of these bulk materials in high energy ball mill for obtaining nanomaterial size, right? And for that, we need something of a parameter called critical speed. For a ball mill to operate, critical speed needs to be achieved. Now, what is critical speed? Critical speed is the minimum amount of speed below which nanoparticle size cannot be achieved. So the outer ball needs to rotate in a particular speed above which, that is the threshold. Above that speed, we can obtain nanomaterial sized. So the force of collision will be greater and we can obtain smaller size of particles. The enclosed ball begins to rotate along the inner walls of the ball mill, as we have already discussed. Now, what happens when it fails to reach the critical speed? If it fails to reach the critical speed, it will remain stationary at the bottom where they have no impact on the material. So there are now technologies where if critical speed is not met, the rolling ball will stay at the bottom where they have no impact on the material. Now the material will not reach, it will grind, but it will not reach the nanoparticle size where we need the nanomaterial synthesis to happen. And the form of physical entity this ball milling follows is mechanical pressure. We saw four forms of, if we go back, we saw four forms of physical methods here. So the first, ball milling operates on mechanical pressure basis, right? Yes. Now let's look at what is electrospraying technique. So in this electrospraying technique, so if you follow this diagram A, this is a syringe here connected to the syringe pump, and inside this syringe, this blue color solution is the polymer solution or nanomaterial synthesizing solution from which we are going to use as bulk material. So if we make it as a solution and pour it into the syringe, this nozzle that we see now will channel this liquid in high pressure to the Taylor cone. So Taylor cone is a specific structure which helps in forming spray droplets. So through high pressure, this fluid containing all the nanomaterial starting synthesis uh, starting synthesis elements will pass through the nozzle, go inside the Taylor cone, where they will, under high pressure, they will form droplets. Now these droplets will be very small in size depending on the size of Taylor cone. And this Taylor cone and the collector is where there will be deposition of these droplets and formation of the nanomaterial. So between this collector and Taylor cone, there will be a voltage difference. So basically there will be electric current which will now guide these droplets to form a deposition on the collector. So if we learn about, if we so there are different modes of spraying, electrospraying, and depending on the voltage there can be variations, and depending on the size of, there can be dripping method, micro dipping method, spindle, cone jet, and multi jet. So these are all modes of electrospraying in which the starting nanomaterial solution is sprayed onto, through the Taylor cone onto the collector in the presence of kilovolt voltage. Here shows increasing voltage, in the presence of voltage, to form a deposition of nanomaterial. So if you see this schematic again, so the Taylor cone somewhat looks like this: charged Taylor cone here because voltage difference, and these are the nanoparticles or in the solution. Now there will be a formation of charged droplet that we see here when the under high pressure droplets would form and in the spray. And then this charged droplet, there will be solvent evaporation. So unnecessary solvent, the solvent material in which the solute is a nanomaterial synthesizer, so in which the bulk material is dissolved, solvent will evaporate, and after evaporation of solvent there will be coulombic explosion. So all these particles will then individually coat with the charges through this voltage difference. Now all these charges will go into the collector plate with the negative potential and deposit as nanomaterials. So we see from bulk material, where we have dissolved the bulk material in a particular solvent, through the Taylor cone we achieve a charged droplet, then the solvent evaporates, then there is Coulombic explosion, a phenomenon in which each individual nanoparticle is coated with the charge, and now these charged nanoparticles will get deposited on a thin film or collector where they will form the nanomaterial. So this is the whole method of electrospraying, and the spray can be controlled through the Taylor cone. It can be drip, it can form a large droplet called dripping, micro dripping, spindle, cone jet, multi-jet. So these are different kinds of sprays which we can use through adjustment of the Taylor cone and depending on the voltage applied between the collector and the Taylor cone. And we feed the bulk nanomaterial dissolved in a solvent through this connected series pump. And this is the method of electrospraying, right? Yeah, I would request again participants to please mute their mic. So here, this physical method uses the form of electrical energy to deposit nanomaterials. So out of four energy types, we saw mechanical process, high energy ball milling, and electrospraying uses electrical energy. Of course, this voltage is what causes nanomaterial deposition on the collector. Now coming to polyol synthesis, which was the answer for this question. Which of these is not a physical method of synthesis? So in polyol synthesis, to start with, what is a polyol? A polyol is an organic compound containing multiple hydroxyl groups. So any organic compound consisting of carbon backbone with large number of hydroxyl group is called a polyol. So hydroxyl group containing elements, organic compound, are called alcohol. So polyol means multiple hydroxyl groups. So it's an alcohol with lots of OH, right? So here is an example where we use triethylene glycol as the polyol with lanthanum chloride or lanthanum nitrate. So this is the synthesis of lanthanum oxide nanoparticles, metal-based oxide nanoparticles using polyol method. So there are various processes involved: magnetic stirring with atmospheric condition dissolve at 80 degrees Celsius. NaOH treatment, then hydrogen peroxide treatment, leading to lanthanum oxide nanoparticles. So in this method, in the polyol synthesis method, all these reactions happen inside a round bottom flask where there is heat supplied along with magnetic stirring and different pressure and temperature conditions, where we stir these solutions in presence of polyol, which is triethylene glycol, TEG here, in presence of other elements to form the metal oxide nanoparticles. And then these metal oxide nanoparticles here is further used with a ligand to coat the nanoparticles, so it can become a ligand coated lanthanum oxide nanoparticles. So this is a process of polyol synthesis in which we use a polyol triethylene glycol to synthesize Ln2O3 nanoparticles. And here is the structure of a polyol. It's a polymer of a compound containing lots of hydroxyl groups. All these O groups marked in red are hydroxyl groups, and they have undergone condensation reaction to form polyesters, polyethers. So a polyol can exist as a polyester with ester group, polyether. This is an example of simple polyol. And this polyol synthesis is not a physical method because it falls under the category of chemical method of synthesis, in which we use chemical as a starting material for synthesis of nanoparticles, right? So we saw in this process, we saw two different physical methods of nanoparticle synthesis: high energy ball milling, which uses mechanical force, and electro spraying, which uses electrical energy, while polyol synthesis falls under the category of chemical methods of synthesis, in which we use triethylene glycol in a round bottom flask to synthesize Ln2O3 nanoparticles, right? Yeah. Is it clear to students the difference between chemical and physical methods and why the answer should be polyol? The students have answered correctly. Option B is the answer, polyol synthesis. Is it clear to students? You can just mention in the chat box. I'll wait for some time for some responses. See, these are all individual methods for nanomaterial synthesis. So it could be difficult for you guys to accumulate it all, but the main principle behind all this is very easy to understand if explained properly. What is the major difference between top-down approach? What is the major differences between physical and chemical methods? So here we encountered two physical methods and a chemical method. Okay, so yes, sir. Four people have responded. Let's move on to the next question without wasting much more time. The next question here is on the screen. Melt mixing is a dash method of nanomaterial synthesis. Melt mixing. Options are physical, chemical, biological, none of the above. Melt mixing is dash method of nanomaterial synthesis. Students, please try to answer. Try to put down your logic. Even if you are guessing it's not correct, it's okay. We will go through all these methods. We'll see what kind of a procedure is melt mixing. Just try to answer. See, we all want maximum participation in this practice assignment so that your concepts gets clear and you are able to solve your assignments on your own, right? Yeah, I'll just wait for some time. Melt mixing is dash method of nanomaterial synthesis. Okay, so there are variety of answers. Many people are answering physical, some people are with chemical also, biological, biological methods. Somebody else in the comment section have asked me clear eighth question of week 2 assignment. So I would like to answer that as a reviewer or as a TA for this course, your assignments are not yet visible to me, and I'm only here to make you interact with a practice assignment. So I won't be able to solve the eighth question or whatever question from your actual assignment. I cannot help. I'm sorry, I cannot help you with that. But I can. What I can help you with is the concept and concept solving of this practice assignment. Yeah. So see, lots of students are answering now. It's good to see that. Physical method not sure. Either A or B. Some people are confused. So let's see what is the correct answer. The correct answer is physical method. The answer is A. So all the students who have answered A are correct. Melt mixing is a physical method of nanomaterial synthesis. See, it's kind of intuitive. Melt mixing, what do you think could be? Melting, melting a bulk material or melting any material and mixing the properties of two materials or multiple materials to create a nanomaterial, right? So melt mixing is a physical form of nanomaterial synthesis. See, it can be either top down or bottom up approach. That depends on the kind of melt mixing we are performing, right? If the starting material of melt mixing, if the starting material of melt mixing are two nanoparticles again, then that will be a bottom up approach since we are using a smaller template to synthesize another nanomaterial. But if the starting material of mixing is a bulk material, then that will be a top down approach. We are breaking down the bulk material for nanomaterial synthesis. So now let's look at what is the melt mixing process. Yeah. So as you can see on my screen, this is a schematic for melt mixer. So there is a structure called hopper where we feed the polymer. This polymer can be the starting material, it can be the bulk material, or it can be two different nanomaterials. So if you have encountered a type of nanomaterial called nanocomposite, nanocomposites have properties of different nanomaterials in a single particle, right? For synthesis of nanocomposite, we can use two different types of nanopolymers as starting material. Then it would be a bottom up approach since we are using a nanomaterial to synthesize another nanomaterial, right, as a template. But if we use a bulk material in this, then for the nanocomposite, then it will be a top down approach. For nanocomposite, if we use other nanoparticles or polymers, it will be a bottom up approach, right? Then these hopper will then funnel the polymer into a heating conveyor belt. Here it's labeled as twin extruder. So extrusion is the process of extracting the desired polymer or nanomaterial for us, and this chamber is totally heated. So what the heat will do, it will combine the two polymers or whatever the bulk material, it will melt them at melting temperature, melt them and mix them, as the process is named melt mixing. And there are certain filters through which these melt mixing process will pass through, all the liquid or melting process will pass through. And there is something called twin extruders, these brown rods that you can see here. These twin extruders will then absorb or adsorb on the surface, melting the melt mix substance and then coat it as a nanomaterial. And there is a pressurizing system which maintains the internal pressure of this chamber. And twin extruder, so the nanomaterial will be deposited on the surface of twin extruder as a nanocomposite. Since we are using multiple polymers for the feed, we can design a nanomaterial in which there will be multiple properties of different unique nanomaterials. We can combine them with the help of melt mixing with high heat and pressurizing system and collected it as a layer of nanomaterial from this twin extruder, right? So this is the industrial process or how it happens for melt mixing process. The melt mixing consists of dispersing the nanoparticles by mechanical shearing action in the polymer matrix in the molten state. So method this method uses two different physical forces. It's also mechanical shearing as well as heat. So we have thermal energy, use of thermal energy, and molecular shearing also, mechanical forces. This method offers greater facility of preparation because it is based on traditional methods of polymer processing. Okay, so this method offers greater facility of preparation. Traditional methods of polymer processing because we can add two polymers, melt them, infuse their properties, and then so extract the new composite material with both the properties, right? So it is classified as a physical method of nanomaterial synthesis, which was the answer. So melt mixing is a physical method which uses thermal energy and also mechanical shearing. Mechanical force is also an answer, but it is not a biological or chemical method of nanoparticle synthesis, right? Okay, so there is a question in chat box. Which of the following doesn't follow the principle of physical methods? High energy ball milling, high energy ball milling, high energy radiation, mechanical abrasion based techniques for nanoparticle synthesis, and electro spraying. High energy ball milling is under physical methods because it uses mechanical forces. High energy radiation also uses radiation processes. Mechanical abrasion based techniques for nanoparticle. Mechanical abrasion again uses uh, forces like mechanical forces. Electrospraying. Seems like all of these are physical methods, right? Because we are using electrical energy, mechanical energy mostly, and radiation also. Yeah, the question seems like which of the following doesn't follow the principle? Mechanical abrasion based techniques. Mechanical abrasion uses let me just check. Mechanical abrasion. Yeah, mechanical abrasion is a technique in which we use sandpaper and blasting to reduce the sizes of materials. So I think there is a uh, D is answer. Electrospraying. But electrospraying uses electrical energy, right? Electrospraying is a form of physical method of yeah, but electrospraying can also be modified as a chemical form of nanoparticle synthesis, in which, see, if the solution or the solvent in which the nanoparticle is dissolved is changed, and the particles are then charged oppositely. So if we go back to electrospraying here, as mentioned, electrospraying is a physical form. It uses electrical energy. So here in the connected syringe pump, when we are loading the nanoparticle synthesizing material in solvent form, here if there can be different chemical starting molecules, right? So this can also be modified as a physical technique to a chemical technique. So might be that is the reason why D was the option, but I don't think mechanical abrasion, high energy radiation, or high energy ball milling would be an option. I hope it clears your doubt, because electrospraying can be modified for a chemical way also. If we change the properties of these particles, the synthesizing particle, if we use, like we started with polyol synthesis, right? If we use polyol as a starting material, then it obviously is a chemical method. Yeah. Yeah, let's not I'm sorry, but let's not move on to solving personal doubts. Let's first, I'm sorry, Rashmi Singh. Let's first finish this. If time permits, we can. Because what I am supposed to do here is guide you through with your doubts and your assignment. Here is the practice assignment that I'll be solving. So maybe you can post this question to the instructor or to the NPTEL, or if I have time, I'll take it up. Let's first finish the ninth question. So is it clear to the students about melt mixing and the question number 8? If it's clear, then we can move on to the next question. Yes, so okay. Let's move on to the next question here. Question number 9. Which of these is not a chemical method of nanomaterial synthesis? Students, please try to answer. Rashmi, after finishing this session, if we have time, I'll take up your question. Please try to focus on the ninth question here. Which of these is not a chemical method of nanomaterial synthesis? Sol gel synthesis, micro emulsion technique, chemical vapor synthesis, or laser pyrolysis? I'll wait for students to try to solve this question. Please, students, show some participation and try to guess the answer even if it's not correct. We will learn about the correct answer. Which of these is not a chemical method of nanomaterial synthesis? Sol gel synthesis, microemulsion technique, chemical vapor synthesis, and laser pyrolysis. I'll just wait for a minute to accumulate some answers. Okay, there are some answers. Most of them have answered D, laser pyrolysis. Laser pyrolysis. Let's see what is the correct answer. All the students have answered very nicely. Is the correct answer laser pyrolysis? There is even a student saying laser pyrolysis is a physical technique, which is absolutely correct. Laser pyrolysis is a physical technique. It's not a chemical method of nanomaterial synthesis. So here is a schematic showing the arrangement of laser pyrolysis setup, in which we have a laser source here. Mostly, generally, it is carbon dioxide laser set. This laser then passes through the lens, and here at the intersection, there are some gas inlets which will let in the gas, like carbon dioxide, as I mentioned. Laser pyrolysis is a process in which continuous wave CO2 laser is used to heat flowing reactant gases. So reactant gases, whatever we are trying as a starting material, those gases will be sent in, and this high power sources will heat the gases, resulting in molecular decomposition to form vapors to initiate nucleation and followed by the growth of nanoparticles. So what is our objective here at this junction or flame point in the chamber? These gas molecules will then be decomposed to form vapors of different varieties of nanoparticles. When you decompose a gas, or when suppose we have carbon dioxide gas and we are decomposing it, so it will form smaller atoms, atomic sizes of nanoparticles in the presence of this high energy laser source. And then this small nanoparticles can then be allowed to nucleate, or as I was explaining, to form self assembly or clustering initiation reactions or nucleation, which will then grow, which will then be followed by the growth of nanoparticles, and these nanoparticles grow to deposit as nanomaterials or nanoparticles, which will be then collected through this stream. Here is the sample collector filter. So on this filter, these stream of nanoparticles which have already started nucleation will start depositing, right? And this vacuum pump will then just maintain anaerobic conditions here, devoid of air. So in the influence of high laser power, these gases will decompose and then turn into nucleation centers, vapors, which will then nucleate, then deposit all these nanoparticles on the sample collector filter. So this is the process of laser pyrolysis. So always pyrolysis means heat. Pyro means heat element. So pyrolysis is a physical process in which we use thermal energy again, right? So at the crossing point of this laser beam and gas inlet, the laser energy is absorbed by the gases, leading to molecular decomposition, right? Laser energy will be absorbed by these gases, molecules, and these molecules decompose into nanostructures or to form vapors. And when nuclei reach the critical stage, these are called nuclei, these molecular decomposition, nucleation centers. When nuclei reach the critical stage, fast homogeneous nucleation takes place, which further leads to growth of nanoparticles. And then these nanoparticles are transported to collecting bag using inert gas. So this vacuum pump and all will provide an inert gas and circulate it, while these nanoparticles which have started nucleation from the vapor state will be collected on the sample collector filter. And as we have understood, this uses thermal energy from the laser, and it is also one of the physical methods, as somebody in the comment correctly mentioned. So laser pyrolysis is a physical method, which is the answer to the question which of these is not a chemical method. Here, sol gel synthesis, microemulsion technique are all chemical methods. Chemical vapor synthesis, right? Students, is it clear? Is it understandable? You can just type yes, so we can proceed. I'll wait for a few minutes. Is it understandable? If not, then you can stop me and I'll explain it again. There is no, that is not a big issue. Yeah, seems okay. Yes, sir. Okay. So people are able to understand. It's good to know. Now for the final question, let's move to the final question. Which of the following is an advantage of biological methods of nanomaterial synthesis? So far, we have dealt with physical methods. We have seen some chemical methods. Now, there is a question. Which of the following is an advantage of biological methods of nanomaterial synthesis? Options: low toxicity, low sustainability, poor efficiency, low biodegradability. I'll wait for a minute for students to answer. Please just try to answer. We have already reached the last question of this practice assignment. Okay, there are already some answers, right? Many people have answered option A. Sonali has said option B. Any other school of opinions? Students thinking something else can be the answer? Either it's A, B, C, or D. I'm sorry, Rashmi, this is the duration that I have been allotted. So, this class, I know it's very lengthy, but there are no more questions I receive only 10 questions as practice assignment for a week, which is relative to the lectures, and we have to understand it uh, well so that we clear our concepts for 2 hours. You have to bear with me. If you answer this question correctly, then I might look at your question. I think we'll have some time. Okay, there are already some answers. Let's move forward. Low toxicity and low sustainability. So two options, right? People have voted for. The answer is option A, low toxicity. Which of the following is an advantage of biological methods, right? So technically the only advantage here, if you see of all the four options, it's low toxicity. Low sustainability might not be an advantage as such. Poor efficiency is also not an advantage. Low biodegradability also. That is a like crude way of answering this question. But we'll see what is the why low toxicity is the advantage. So using biological materials such as bacteria, yeast, molds, microalgae, and plant extract to synthesize, nanoparticles have some advantages. So in biological methods, we use bacteria, yeast, molds, microalgae, and plant extract. So uh, we use microorganisms or living things or biological systems as the starting material for nanomaterial synthesis. We do not use bulk minerals or ores or any other polymers or chemicals. So those fall under the category of physical and chemical synthesis. In biological synthesis, we have bacteria, yeast, and all to start with. And what this process has an advantage over others, it consumes very low energy because maintenance of biological organisms is quite low. If we have microbes maintenance are very low energy consumption. Moderate technology, we do not need any high-end technology like electrospraying or melt mixing or ball rolling. We just need to provide a container or a bioreactor in which all these organisms can grow and synthesize the nanomaterials, right? We do not need very high-end technology. We need moderate technology is also fine. No toxic chemicals. So no toxic chemicals need to be applied. So it's very safe to handle as a biological method of synthesis. Of course, yeast, bacteria, and all pathogenic bacteria are not used for nanoparticle synthesis, but stuff like E. coli and all we can easily handle, right? And these are some of the applications we see of biological synthesis of nanoparticles. So there can be microorganisms which produces enzymes like nitrate reductase, naphthalenoquinones, actinomycetes, yeast, bacteria, fungi. All of these microorganisms can be used as biological material for synthesis, and they have many enzymes like naphthoquinones, anthraquinones, synthesis, metal salts, metal nanoparticles can be used. Plant tissues like leaves, stem, fruit, flower can all are all sources of proteins, amino acid, vitamins, polysaccharides. So these can act as starting material for the nanoparticle synthesis. Plant extract, leaf extract, bacteria, fungi can also provide all these materials. And then this can be and then this can be used in applications like antimicrobial, antipathogen, mosquitocidal uses, right? Because these nanoparticles can just deliver antimicrobial agents and kill any infection. So many nanotechnology based medicines have now developed which can treat microbial infections, pathogen infections, and mosquitocidal uses. We can use it on spray it on ponds and all to kill mosquitoes. Cosmetics and medical appliances. Many nanotechnology, nanomaterial based uses used in cosmetic and medical appliances to effective delivery of whatever enzymes and particles that we need. Photo imaging, photothermal therapy, magnetic responsive drug delivery. So nanoparticles form an excellent basis for drug delivery, right? Various types of human cancer where we can use biological synthesized nanoparticles because they are synthesized from living materials or biological synthesized, they have lesser side effects. Nanosensors detect biomolecules, environmental factors, cell labeling, and gene delivery. Right? All these applications can be from biological synthesis of nanoparticles. Is it clear to the students? Is it clear to the students? You can just type yes or no in the chat box. Yes, good, good, good. With this, we have come to the end of our practice assignment. Now we have some time left. There was a question in the chat box. I would like to take that. I think it was Rashmi. Could you please post the question? Yeah. So match the following, right? Table 1 contains methods for synthesis and table 2 contains the techniques. Physical method. So we just now learned high energy radiation is a physical method for synthesis, right? So let me just stop sharing and talk to you directly. Stop presenting. Yeah, let me turn on. Okay, so everyone, please focus on the question in the chat box posted by a student. Physical method of synthesis. So which will be the correct answer? It's definitely high energy radiation because it's a physical method of we use high energy radiation to break down bulk materials, right? In a top down approach. Chemical methods. So micro emulsion technique we just now encountered in one of our questions, that micro emulsion, sol gel, and chemical vapor depositions are all chemical methods of synthesis. Polyol synthesis, definitely a chemical method of synthesis. We use ethylene glycol in the example. Try ethylene glycol as a starting material along with lanthanum chloride to form lanthanum oxide nanoparticles, right? So the answer will be physical energy A to high energy radiation number 2, chemical energy microemulsion technique and polyol synthesis, and there is no example of biological synthesis here. If there had been a DNA primer synthesis or something involving a microorganism, that could have been a biological technique, right, or a bioreactor. So the answer will be A second option, B first option, and B third option. So Rashmi, I hope you got your answer. Biological technique will not be a high energy radiation technique, right? The answer that you have mentioned. I think accepted answer is A2, B1, and B3. How will we match B option with first and second? No, the answer is chemical microemulsion technique and polyol synthesis. So 1 and 3 will match with B and 2 will match with A. So that is the answer. Yeah, I hope your doubts are clear. Okay, there are also some other interesting things in the comment section. If we talk about nanoparticles in soil in form of fertilizer, then it should not sustainable, otherwise it will harm our soil. Is this regarding to any question? If we talk about nanoparticles in soil in the form of fertilizer, see Sonali, we always have to find out a fine balance between what is more advantageous. Nanoparticle fertilizer is definitely better than chemical fertilizer. See, if you argue on that point, then chemical fertilizer is also not sustainable for the soil. But what is the advantage that nano fertilizer is giving? So let's say if I want to synthesize a nanoparticle based fertilizer and I start with a biological method of synthesis, then I'll use organic templates like yeast and fungi. Let's say use plant extract for designing that fertilizer and synthesize a nanomaterial based fertilizer. Now what will happen? Why nanotechnology is so relevant in agriculture? The nanomaterials will provide higher surface area for absorption. So that's what lacks in a chemical fertilizer. On the surface of nano fertilizer there will be lot of absorption, so the plants will be effectively absorbing the fertilizer. So the same amount of, if you imagine in a broad way, 1 kg of a chemical fertilizer used in the soil will give X amount of nutrition. Then lesser than that amount of nanoparticles, maybe 1 gram of nanoparticles would give achieve the same effect. So only 1 gram of nanoparticle could give the same effect because of its surface absorption. The size is so small, now the fertilizer can be absorbed easily in the soil. And definitely it's not sustainable. Using any kind of fertilizer is not sustainable other than organic farming. But we have to make a balance, right? Instead of using chemical fertilizer directly, we can use nanoparticle based fertilizer to increase the surface area, so that we require lesser amount of fertilizer. I hope that helped. Yeah, thank you. It's already 5 p.m. It's good to see that students have participated well. See you in the next practice assignment session where we'll solve week 3 assignment. I hope this assignment session is helping you in understanding the lectures. Okay, thank you. I'll end the meeting now. Bye bye. Take care.